Welcome! Many applications in linear algebra involve multiplications of matrices. This can be a tedious task, especially if the matrices involved are large, or if you need to take high powers of a matrix. In this video, I would like to show you a tool that can simplify calculations, the diagonalization of a matrix. Let's start with the definition. Let A be an n by n matrix. Then A is called diagonalizable if it can be written as a product P times D times P inverse, with P an invertible matrix and D a diagonal matrix. In this situation, the decomposition P times D times P inverse is called a diagonalization of A. Let me give you an example to illustrate the definition. Consider this matrix. A diagonalization of matrix A is given by the following product, where D is the diagonal matrix in the middle and P is the invertible matrix 3, 1, 4, 1. I invite you to pause the video and check yourself that this product is indeed equal to A. Of course, you may wonder how to find such a diagonalization. I will address this question later in this video. First, let me give an example of how a diagonalization can simplify calculations. Let's stick with the diagonalization given. Now, suppose you want to calculate A to the power 10. Even for a 2 by 2 matrix, this is quite a lot of work, especially if you do it by hand. However, we have a diagonalization of A, and my claim is that this will make things easier. Let's expand the product. Make sure that you do not interchange the order of the matrices in the process. You see that you get several occurrences of P inverse times P. But P inverse times P is equal to the identity matrix. P and P inverse cancel. This means that the product simplifies to P times D to the power 10 times P inverse. Explicitly, we get this. So instead of having to calculate A to the power 10, we must calculate the 10th power of a diagonal matrix. But that is easy. It comes down to taking the 10th power of each diagonal element. Note that this is only true for diagonal matrices. Now we can do the calculation by hand. Check yourself that you get this expression. The entries may look a bit frightening, but they are just numbers. If you calculate the powers, you find this matrix. Of course, there's nothing special about the 10th power. We can calculate relatively easily any power of A in this way. We could even find a general expression for the nth power. These kind of calculations typically occur in the analysis of discrete dynamical systems. Now, let me return to the question how to find a diagonalization. For this, the following theorem is important. Let A be an n times n matrix, then the following two statements are equivalent. 1. A has a diagonalization P times D times P inverse with invertible matrix P and diagonal matrix D. And 2. P has columns V1 to Vn and D has diagonal elements lambda 1 to lambda n, where V1 to Vn are a linearly independent set of eigenvectors of A with corresponding eigenvalues lambda 1 to lambda n. That is, lambda 1 is the eigenvalue of V1, lambda 2 the eigenvalue of V2, etc. You will find the proof later on in this section. For now, let's check that the theorem applies in the example that you saw earlier. The first column of P should be an eigenvector of A with eigenvalue -1. We can easily check this. Matrix A times the first column is equal to the vector -3, -4, which is -1 times the first column of P. So indeed, the first column of P is an eigenvector, and the eigenvalue is the first diagonal element of D. Similarly, the second column of P should be an eigenvector of A with eigenvalue 2. Let's check. A times the second column is equal to the vector 2, 2, which is indeed 2 times the second column of P. Again, it checks out. The theorem gives a procedure to find a diagonalization of a given matrix. Given a matrix A, find the eigenvalues and eigenvectors. From these, construct matrix P and matrix D, and then these matrices will give a diagonalization of A. I'd like to end with 2 remarks about the theorem. First, it is important that B and D match. By that I mean that the first diagonal element of D should be the eigenvalue of the first column of P The second diagonal element of D should be the eigenvalue of the second column of P, etc. But other than that, you can use any independent set of eigenvectors and the corresponding eigenvalues. And this means that diagonalizations are not unique. For example, we saw this diagonalization. The second column of P is an eigenvector of A with eigenvalue 2. But we can replace it by any other eigenvector with eigenvalue 2. For example, the vector 7, 7. Also, we could interchange the order of the columns of P. They are still an independent set of eigenvectors of A. However, then we must interchange the elements of D as well. You can check yourself that these are indeed 3 diagonalizations of the same matrix A. As a last remark, let me stress that for a diagonalization of an n by n matrix, you need a set of n linearly independent eigenvectors. Otherwise, matrix P cannot be invertible. It is not always possible to find such a set of eigenvectors. For example, consider this matrix. You can check that it has only one eigenvalue, namely lambda equal to 1. The eigenspace turns out to be spanned by one vector, the vector 1, 0. That means that all eigenvectors of A are a multiple of the vector 1, 0. In particular, it is not possible to find 2 independent eigenvectors. That means that this matrix is not diagonalizable. We will come back to the issue of diagonalizability later on in this section. Okay, that was a lot of information. I encourage you to do the exercises to get a feeling for the concept of diagonalization. Good luck.